multi-core operating system. So last time we were in the middle of multi-core. So I think again, I think one thing I want to talk about briefly before we start is when I was undergraduate, when I started learning about programming and OS, so I learned about similar concepts like synchronization, multi-threaded programming, and at the beginning I was, at least at that time, I was not aware why people in the industry, like mature developers and researchers, always see that synchronization or concurrency is difficult. So one of the reasons is that the homework assignments that we do in undergraduate is extremely simple compared to the real world concurrency issues that we're running into. Okay, and at least at that time, right? So when I was an undergraduate, I learned this concept. I was not that attracted to it because I felt it was simple. It was not intellectually stimulating. But you will realize, right? So after learning these basic concepts, once you get into more serious system design, and once you start designing a completely new multi-threaded application yourself or a distributed system yourself, will design how they interact and how they coordinate. That's when you realize how difficult it is. So before I start designing my own first, actually let me even put it this way. When I was doing my graduate school, I started designing this distributed system from scratch, but because there were courses that are difficult courses that ask you to write a distributed application yourself. Even then, it was not that challenging because I was following the protocols that already exist. Right? So there are many mature protocols, distributed protocols that tells you how you should design the different threads and nodes interact with each other. I felt it was challenging, right? So that's when I felt it's difficult. But it's not just following the protocols. Make sure that you are not deviating too much from the theoretical concept, and following the overall protocol and implement some prototype that follows the protocol and maybe do not have too bad performance. Right? That's challenging already, but still not that difficult. Still did not help me to realize why there's so much research going on into this kind of topic. Right? So it's until I started designing a new protocol myself. Right? So when I started designing a new, I have a goal that I want to reach. I started designing this new distributed system and protocol by myself, and I constantly hitting dead end. Right? So I thought I have a smart idea. I'm just going to go this way. And after reasoning along this line for a while, I realized that okay, people have thought about this. There's some concurrency issues on this direction that just doesn't work. Right? And yeah, so I keep hitting dead ends, and until I find some new protocol that really make it work. Right? So that experience really made me realize, right? So why people, mature developers and researchers, always see that concurrency is difficult. It is, right? It's just I think you probably need to go through a few stages before you really realize how difficult it is, why it is difficult. yeah, so from the announcements that you have as an undergraduate student in undergraduate courses, so probably, at least when I was an undergraduate student, I didn't feel it was that difficult. Yeah, so if you're more interested in this kind of a topic, I'm teaching distributed system next semester. So we do have a lab that asks you to write a distributed system yourself, following known protocols, so it's not super difficult. But yeah, I think it's enough to give you a understanding, right, why this kind of topic is difficult. Okay, yeah, so I think back when I was an undergraduate student, when the instructors were talking about multi-core OS, I was saying, okay, yeah, so you had one CPU, now you have multiple, right? So in one machine, what's a big deal? Right? So why it's such a big deal? So it is, right? So both because it's very difficult to get a multi-core system to work correctly, and also multi-core really, if you make a multi-core system work correctly, it really beats single-core systems. Right? Performance benefit is huge. Okay. All right. Yeah. So I think the research that went into the multi-core OS it's still going on. Right. So I started. I think it becomes a hot topic 1980s around that time, and even nowadays, right? Multi-core. There are still a lot of unresolved problems in multi-core, and it's still a very hot research topic. Okay, so now I give everyone a bit of motivation, right? Why this is interesting, why it's challenging. Let's talk about multi-core OS again. Right? So I think where we were. Okay, yeah. So let's start from what a multi-core system looks like. Right? So in a multi-core, in a single chip that contains multiple identical processors. So it's remember the point is that these cores are on the single chip, and because they are on the same chip, so their communication is very fast. Right? Okay. So there is a on-chip interconnection mechanism that allows them to communicate and share data. So the reason that this is important is that before multi-core, people tried putting multiple processors in one machine, but just not putting them on the same chip. Okay, people have this design, and I think it's not called, right? So it's called parallel computers or parallel computing. Okay, so people put multiple CPUs, processors in one computer. But it didn't work well, right? Because they need to communicate through the normal bus inside the computer, and the speed is not ideal. Okay, so multi-core is when you put multiple processors on the same chip, and in the same chip, the interconnection is very fast compared to the other bus in the machine. Okay. And this turns out to be very important and made the system to work efficiently. Okay. Yeah, so there are some subtleties, right? So usually you start one core when the chip boots, and you allow this core to start the other cores. So there will be one special core 0. It differs slightly because it needs to be the first one to start, and it needs to start the other cores. Okay. So this is the architecture of a multi-core CPU. You have multiple cores, and each core has their own local cache, right? This is usually L1 cache. Okay, and these caches, they have a shared onboard bus. This is the bus in the chip that is different from the external bus in the machine. Right? So this is a bus that's very fast. Okay, and you usually, right, in modern CPU, you also have a shared L2 and L3 caches. Right? So a larger cache that's not local to every core. So those caches are shared by multiple cores. Okay. So you allow groups of cores to share L2 cache, and you also allow all the cores to share L3 cache. Right? That's a typical design. And this, I think we mentioned last time, this design brings a problem cache coherence. Right? So the different CPUs, they have their local cache, and this local cache might cache the same memory, the data stored in the same memory address. And maybe one thread wants to use a variable A, and that thread is scheduled to execute on core 0. And there is another thread scheduled to execute on core 1, and they have a shared variable, and that variable is shared between them. So during their execution, they will both load this shared variable into their local cache for their execution. How to make sure that the variable's value is consistent between these caches? That is cache coherence. Okay. Some manufacturers offer specialized communication channel that allows a core to send a message to another core, and a core to broadcast a message to all other cores. Right? So this problem, communication between CPUs, right? So or between processors, has been studied extensively in theory. Right? So it's called multicast. It's one-to-one communication, is a point cast. Right? So how do you send one message from one processor to another? And broadcast is a special form of multicast. Right? So broadcast means that there's a group of processor, one processor sends a message and it will be sent to all the other processors. And multicast is a more general concept of this. It says that you have a set of processors. Multicast allows you to send a message to a subset of these processors. And it sounds easy, right? It sounds like just sending a message or sending multiple messages. But the subtlety exists in how do you make sure that this broadcast message all arrive. Right? So if I want to broadcast a message to all the processors, I want to make sure that they receive all my messages ideally in the same order. Right? So I want to guarantee that these messages are all received, and I want to guarantee that these messages are received in the same order. And this is turns out to be extremely difficult. Okay, there's a complete line of research, decades of research into just this problem, multicast. Okay, yeah, but. People have figured out some algorithm, and the hardware manufacturers have built these algorithms into their hardware. Right? How to do send one message. That is easy, but both broadcast and multicast is difficult. Okay, but people have implemented that. Okay. All right. So some other manufacturers use interrupt-like. So this is similar to, this is slightly different message. This says that one core can interrupt the other core and tell it to do something. Okay. All right. So now cache coherence. We in multi-core, I think one of the most important problems, right? One of the most important research problems is cache coherence. So, which I just mentioned, that this is a more concrete example. Right? So we have a core 0 initialize a shared variable x to 0, and the core 1 access this shared variable, placing this 0 in its local cache. Right? Maybe this core 1 is running thread 1 using the shared variable. And core 2, right, running another thread 2, it also shares this variable x, and also place this 0 to x. And core 1 increments x, writing 1 to its memory, and core 2 access x and obtain 0 from this local cache. Right? How to avoid this problem to happen, and more importantly, how do we define the desired semantic of this concurrent execution? And when you have a shared variable, and there are multiple cores accessing this shared variable, what is the semantic guarantee that you want to provide to this set of cores? Right. For example, do you want to provide atomicity, meaning that if there is one core that modifies the variable, the other cores need to know it? Right, that's one possible semantic, right, atomicity. Or some application might be fine with this. Right? Some application might be saying that, okay, I have multiple processes, each of them is modifying their own snapshot of a variable, and that's okay to that application. This is also an acceptable semantic for many type of applications, right? It's sometimes it's typically called snapshot isolation in the databases. So, right, so these is sometimes acceptable to some applications, but for most of the applications, you don't want this. You want serializability. Okay, you want the all the operations that from different cores to one shared variable to be serializable to that variable. So what does serializability mean? It means that all the operations from different cores that happen to this shared variable happen as if that they happen in a serial order of all the operations. Okay, in this case it doesn't. Because if this operation happen in a serial order, right, so the core 2 would see, actually this case also this case also satisfies serializability. It happens as if the core 2, but the order is split, right? So you can see that this core 2, although it accesses X after step 4, so it sees this value 0, but in a hypothetical history of serial execution, you can imagine core 2's read happened before the step 4. Right? So if we reorder, right? So step 1, 2, 3, 5, 4, then this is a valid serial order of operations that happen to X in history. Yeah, so this is not an example that violates serializability. If core 2 also increments X, that will be a history that violates serializability. Okay. Anyway, so we won't dive into too much detail of this. Right? So serializability, snapshot isolation, these are more advanced topics that you will learn about if you take either database course or distributed system course. Right? So I'm just giving you guys a brief idea. So the point is that so we want to decide what is the semantic that the CPUs, the multi-core CPUs will support when there are shared variable accesses. And typically, people want some kind of serializability. And serializability is very difficult to achieve. Okay. Right, so coordination, right? So here, I think in this slide, there are a lot of texts, but so the point is that there are some simple way to achieve this the serializability. Right? So I think let's go back to this example. Right? The simplest way we explained last time is that when core 1 increments X writing value 1 to its memory, you will see that this cache line is dirty. And because this cache line is dirty, it will immediately invalidate all the corresponding cache lines in the other cores. So when core 2 access X in step 5, it will see that my cache line is invalidated. So I cannot just read the 0. I need to refresh X value by reloading it from memory, for example. Okay. All right. So that is the simplest example of cache coherence protocol. If you have a core that writes a value to a cache line, it will invalidate all the other cores corresponding cache lines. Yeah, so core have, so the cores need to coordinate to avoid risk conditions that we just explained, and typical coordination, mutual exclusion locks with basic weighting. Okay, and we explained this before. Right? Spin locks, mutual exclusion locks with basic weighting has negative effects. Right? It first reduces parallelism. Right? When you use spin locks, it means that only one core. Right? Although you have multiple cores that who can execute in parallel, but only one of the core can really proceed, right? Because of spin lock. Right? One core is busy waiting, the other core is not computing. Okay. Second, waste energy. Right? When it runs in a busy wait loop, the core continues to consume power even though it's not performing any useful computation. Yeah, so we also learned that disabling interrupts is one approach to coordinate between threads, but it only works in single core CPU. Right? So if one thread wants to use the CPU to perform its computation for some critical section, in single core you can turn off the interrupts on this core. But in multi-core, one core is not allowed to turn off the interrupt on the other core. Okay. That is invasive. So, so the ability to turn off interrupts on the other core does not exist. Right. Right. So, yeah, because you cannot disable the interrupts on the other cores, disabling interrupt only on one core does not provide a synchronization for your critical section. So disabling interrupt does not work. Okay, so you cannot use disabling interrupt to protect your critical section. Right. So spin lock works, but it has its downsides. Disabling interrupts does not really work. Okay. So the surprising coordination technology, or actually very often how the test and set or compare and swap hardware instruction is supported. Right? It's actually through this cache coherence protocol we just explained. Okay, because remember that the cache coherence protocol guarantees that when you have a shared variable among all of the cores, when one of the core updates this shared variable, all the other cores will know it immediately. Right? There will be the simplest example is there will be an invalidation that's sent by this core to all the other cores. Okay, so the you can use this mechanism to implement a spin lock, for example. Okay? So that if this, when you use this shared variable and this shared variable is 1 on core 0, for example, and the core 0 is essentially holding this lock, all the other cores, because it got the invalidation message, they cannot proceed. Right? They cannot access this critical section. Right? That's one interesting coordination strategy, right? Using this cache coherence protocol, because a shared variable is coordinated among all the cores. When any write to this shared variable will trigger an invalidation to all the other cores immediately. You can use this mechanism to do coordination. Okay? Yeah. Right. So this is what I explained was a high-level concept. This is a more detailed explanation of how it's achieved. Right? So let's go through it. Right? So you can have a core that locks the memory location, and if other cores try to lock the location, the lock will fail. Right? Why? Because this lock is a shared variable, and if there is another core try to lock the location, it will know that the first core, it has that cache line as 30. Okay. Right. So the other cores will continue trying to lock location, but they will wait, right? Because the first core still has its cache line at 30. Okay. So when the first core holds the lock, release the lock, that's when it writes back its cache line and says that, okay, now my my cache line is not 30 anymore, and you guys can proceed. Okay, and the hardware guarantees that only one other core will be able to obtain the lock, right? Because the next core who grab the lock will invalidate, like simply send the invalidation message to all the other cores to let them know that I have this cache line that is dirty. Okay. Right. So that is how you can utilize cache coherence protocol to build this to build the spin lock. Right? You essentially build a spin lock on top of a cache coherence mechanism. Okay. Right. So each processor includes a special instruction for locking. Right. So test and set or compare and swap. So the sometimes have different semantics. Test and set and compare and swap, they are slightly different, but they are able to achieve the same thing. Okay. And test and set performs two operations on the memory location atomically. It records the value stored in the location and sets the value to 1. Okay. And it reports success if the previous value was 0, and it will return failure if the previous value is 1. Okay, so if a multi-core uses test and set on the same memory location, because of a cache coherence protocol, if the location contains a non-zero value before attempt, the test and set instruction in all cores will report failure. So essentially, this non-zero location in that core 0 will tell the other, I have my cache line 30. Okay, you guys cannot continue. Okay. So if the location contains 0 before the attempt, meaning that its cache line is clean, then the test and set on exactly one core will succeed and fill in all the other cores. Because one of the core will be able to write to that cache line and mark it as dirty. And all the other cores will get a message saying that, okay, there's one core who has its cache line as dirty. Otherwise, other guys cannot write to this cache line concurrently. Okay, so this is how test and set is built. Right? So I think you guys have learned about this test and set in hardware instruction probably in a few different courses, like in computer architecture, and in system programming probably. You have heard about this test and set, right? But how it's really implemented, right? It's implemented on top of the cache coherence protocol. Okay. Yeah. Distributed versus multi-core systems. Okay, so what is the difference between distributed and multi-core systems? It's listed here, but anyone want to take a guess? It's listed here, but anyone want to try to explain that? Yes.
Without illusion, to me, when you say distributed versus multi-core, I think of multiple devices at each with their own independent storage and memory, and maybe more CPUs controlling those, and getting
So we have just learned that multi-core means that you have multiple processors sitting on the same chip. Distributed system means that you have multiple machines communicating through network. Each machine could be a single core system or multi-core system. So that is the difference. And this difference is easy to explain here, but the consequence is actually quite different. So can you imagine what is the consequence? So designing a distributed system is actually much even more difficult than designing a multi-core system. Yes.
You don't have necessarily control over each machine, like their OS can't communicate as nicely, or like they might be working over networks or something.
That's a good guess, right? So they don't have a OS that control their OS control each machine. They don't control each other. Right? Yeah. So people have tried to build a distributed OS, an OS that manage all the machines. Right? So you can actually build a distributed OS. So but that's a good guess. I think the other thing that you mentioned is true, right? So communication through network is slow. Right? It's much slower compared to communication between processors on the same chip. Much slower. That definitely changes how you can design your system. Right? But that consequence is more about you need to do different trade-offs. That's a less theoretical blocker. So theoretically, if you only consider the network communication, the delay in network communication, then you are just doing the different trade-offs. The theoretical challenge that you face is still the same. There's one thing that is that really changes how you view the system. Right? The fundamental difference between distributed system and multi-core system. Yes.
Is it just like fault tolerance?
Exactly, fault tolerance. In multi-core, if there's a core that crashes, your entire CPU will halt, and you will just see that okay, everything failed, and you need to restart. And even if you restart, you have to manually turn off that crash core in order to restart your computer. Right? So all the cores work synchronously, and they assume that each other, not just the cores, the memory system, your disk, everything works. That's connected on the bus works correctly. Okay. Any of them, if any of the core, if it crashes, your entire CPU crashes, affects all the other cores. But in distributed system, it's very different. So when you have tens of thousands of machines running in the data center, every minute there will be some failure. Every minute, every hour, probably every hour there will be a machine that either crash and need to be restarted. Okay, you do not want that kind of failure to prevent your entire distributed system from continuing. Okay, so tolerating these kind of failures makes designing a distributed system completely different from designing this multi-core, multi-threaded applications. Fault tolerance sounds like there's a failure, you handle it, but it's actually very different. Okay, so you will see that in system design, every time you add a dimension, so from single core to multi-core, from single thread to multi-thread, from no fault tolerance to considering fault, failures that can happen independently. Every time you add like one thing, it makes the design of the system, the complexity of your design grow exponentially. Okay, yeah. So so every one of these concepts is actually quite complicated, right? So yeah, so although the physical difference between a single core OS and a distributed system is that a multi-core system is that a multi-core system owns the entire machine, distributed system has multiple machines, but the real difference is in fault tolerance. Okay. Distributed system need to handle faults, need to handle failures, and multi-core system usually assume that if there's one core that crashes, the entire machine will crash, and the user needs to figure out how to overcome the failure. Oh, yeah, so there's another thing. Sorry, I missed one. Yeah. In the distributed system, sometimes you assume that each machine in the distributed system can run different software. Sometimes, right? So, you want to design a system that a distributed system that can still function correctly, even though every machine might be running slightly different software. And how to do that? That is very challenging. So if you have heard about the Byzantine fault tolerance, okay, so that is the theoretical idea that captures this problem. You have a set of machines. Each machine might behave slightly differently, right, because of different reasons. Some of the machines might be running different OS, so their behavior is slightly different. Some might be because, okay, the machine, the software I installed on my machine has a bug. Okay, some because we might be running different versions of the same software. And some could be because one of the machines is malicious. I want to attack the system. So I behave differently. Right? When you have machines in your distributed system that behaves differently, how do you guarantee the nodes that are benign, right? The good nodes, the good machines, can still coordinate to achieve the same goal? Right? That is a Byzantine fault tolerance problem. And if you have heard about Bitcoin, right? So all of these critical currency, these protocols, they are trying to solve this problem. Bitcoin network is an open network. Anyone's machine can join this network as one machine, right, of the entire distributed system. How do you make sure that this entire global distributed system still work correctly? Although many of the machines who join the network want to attack it, right, want to steal Bitcoin. That is a Byzantine fault tolerance problem. Okay. Yeah. So this is the physical difference, but the physical difference between multi-core and distributed system is not the real problem. The real problem is fault tolerance. Okay. The fault tolerance makes a designing a distributed system a completely different monster. Okay. All right. Yeah. Multi-core OS use single OS to control multiple cores. But this is not the core difference, right? So people have built multiple versions of a distributed OS. You have one OS that controls all the machines in within a network. You have tried that. Yeah, researchers have considered several ways to build a multi-core OS. Right? So one core dedicated to OS functions, set of cores dedicated to OS functions or subsystem. All cores run both application and OS functions. Right? This, in the end, all cores run both application and OS function. This is what's adopted in modern operating system. It can use any core. Yeah, so allowing all cores to run both application and OS functions increase performance, but require careful coordination to ensure that only one core attempts to change a given OS data structure at a time. Okay. So yeah, so this is eventually what modern OS really adopts. Okay, so now we'll talk about one concrete example, right? How multi-core OS makes the problem in single core OS much more challenging, right? So this is just one simple example. Right, scheduling. Right? How do a multi-core operating system schedule processes? Okay, so remember, in Xenu, the scheduling is very simple. You have one single core, and this single core every time picks the process that has highest priority from the ready queue. And scheduling policy is very simple. Okay, so in theory we can extend to multi-core, very simple. Right? So they say that if a system has key cores, then at any time key highest priority processes are running among equal priority processes, scheduling is round robin. So essentially, the high level idea is that we have a ready queue, the top key process in the ready queue will be placed on these key cores. That's how naturally you would extend Linux scheduling policy to a multi-core OS. Sounds very simple. Okay. Yeah, but it becomes more complicated when you think about the other complexities, like context switching, caching, and changing cores. Right? So a scheduler that uses round-robin approach and thus advances the process to the next core that becomes available has a surprising consequence. Right? So for example, consider the cache in the data in the L1 cache. When the process runs on the core, the cache fills with data for the process, and when another process starts on the given core, memory references will be expensive because the cache contains items from the previous process. Right? Every core has its local cache. When you do context switch, you need to flush the cache. Right? So when the time slice ends, the scheduler will assign another process to this core, and the cache value will be useless. Every time you do a context switch, all the caches will become useless. Okay, so the cache values, right? They were important. Right? The L1 cache can improve the memory performance by 15 times. So these cache line values, you do not want to frequently flush them out and load in new values for a new thread. You don't want to do that frequently. Okay, so this is one complexity that comes with multi-core. Every core have its own cache, and how do you make sure that the threads can reuse the previous core as much as possible, and because the previous core it was using has its cache values. Okay. How do you make sure that a thread can reuse its previous core as much as possible? This becomes a problem that happens with a multi-core system. In single core, you don't have it. Right? You could still have cache, but you have to do context switch. Right? So every time when you do context switch, you have to do context switch. There's no way to avoid it. But in multi-core, you have this opportunity that you can try to keep the thread to the old core that it was scheduled on. How to exploit this opportunity to reuse the same core as much as possible. And this is one problem that arises with multi-core. Yeah, so the point is that a simplest approach of scheduling the next ready process on whichever core becomes free does not perform well, right? Because it tends to cause all the cache values to be lost during each context switch. Thread affinity, right? So a technique for multi-core schedulers to improve performance. Use the term thread because it helps each individual thread as well as processes. Right? The general idea is to avoid losing the cache values. You want to bind each thread or process to a specific core or set of cores. Right? So again, the idea is very simple. You want a thread to have a higher chance to reuse the core it was scheduled on. It can reuse has a higher chance to reuse the previous core, then you do not lose your L1 cache values. Okay, so when the core becomes free, select the ready thread from the core's affinity set. Yes.
When a thread gets context switched out, does some of this relevant information in the cache stay, or is all of it wiped? Right, because if all of it's wiped, then why does it matter why does it matter if it reads the same core?
If it's you read the same core when you do, then the nominal value was wiped out. Right? So if I have thread 1 scheduled on core 1, right? When I do the next thread want to there's another thread I need to do context switch. I try to reduce. Essentially, I will schedule it onto another thread, another core. Let me think what would be a proper example to show this. Yeah, I think that's a good question. So I think it's not that all the data will be wiped out. It's just that when you context switch in a new thread, the whatever data that's needed by that thread will be loaded. And so there will be some if there are cache lines that are not overwritten, they will still be there. But I need to double check. I need to look into it.
What if that what gets flushed during the context switch?
Oh, and dirty, right?
Yeah.
Dirty cache lines. If that any cache line is dirty, then you context switch out this thread. You need to write those things back. Right. So summary of this affinity scheduling, a multi-core scheduling policy uses a thread affinity as a set of threads to each core and arranges to select from the affinity set when the core becomes free. Right? Okay. And doing so can improve performance because it retains the value in the cache. Okay. So that's one example of the problem that arises with multi-core. But this scheduling, it could mean unfairness. Round robin is fair, but because you do affinity, this could cause unfairness. A low priority thread runs on one core because it is the only thread in the core's affinity set. This is possible. Right? And the higher priority processes remain ready without running because they are not the highest priority processes in their own affinity set. Okay, this happens. Potential solutions make all processes equal priority and keep all affinity sets approximately the same size. Right? Try to average out the consequence. And rebalance affinity sets periodically to prevent severe priority inversions. So there will be some temporary priority inversion, but because you do rebalance periodically, it's not that bad. Okay. So another additional hardware optimization is called simultaneous multi-threading, SMT. Right? So OS assigns multiple threads to one core, and hardware on this core execute instructions from multiple threads simultaneously, provided they do not use the same hardware units in the CPU. I remember the CPU as a pipeline. Right? So if you have taken 250, right, so architecture, each CPU has a pipeline, and this pipeline has 4 or 5 stages, and when you can, which allows you to execute maybe 5 threads at the same time. Right? Thread 1 can be running its instruction in the last stage. Right? Thread 2 can be in the 4th stage, and thread 3 in the 3rd stage, and thread 4 in the 2nd stage, and so so they can run concurrently. Okay, so that is simultaneous multi-threading. Okay, so thread 1 executes a floating point add, thread 2 executes integer write shift, thread 3 stores a value to memory. They are all using different units inside the CPU, so they can run concurrently. This is very standard techniques in a CPU. Okay, so on the multi-core OS, the I/O and device drivers, they are also designed more carefully. You need more control over how to do I/O and device driver. Right? So you cannot allow device driver code for a gaming device to be executed simultaneously by multiple cores. Right? They must use lock to avoid interference. So unless you have, for example, you have multiple hardware devices, you have multiple network cards, and you can let CPU core 0 to use network card 1, and CPU core 1 to use network card 1. Right? So if you only have one hardware, then you need to coordinate how these cores work with this one hardware. If you have multiple hardware, duplicated hardware networks, hardware drives, then you can allow them to work concurrently. Okay. Handling interrupts on the multi-core process has challenges to maximize interrupt performance. An interrupt should be handled by whichever core that is not busy. But if interrupts occur rapidly, two cores may handle successive interrupts in parallel, but writing such code is extremely tricky, and using mutual exclusion among cores is much safer. So the interrupts, because there are multiple cores, when you have multiple interrupts happening, maybe there will be multiple interrupts being handled by each core. So concurrent interrupt handling is very difficult. Okay, so you sometimes when you use mutual exclusion among cores, especially in the interrupt handlers, you need to be very, very careful. Okay, any deadlock, any kind of deadlock in interrupt handlers, the consequences will be very bad. OS designers have found that it's often best to tie a device to one specific core, so that many cores, so the same core handles all the interrupts for the device. Right? This is much simpler. Coordination among cores for the same device, that's very difficult. Okay. So use mutual exclusion in interrupt handler is very, very tricky. So it's interrupt handler is running in OS kernel mode, and there are a lot of trickiness in interrupt handlers. So people typically try to avoid that, and try to. So one approach is to tie one device to a specific one. Additional complications for I/O, right? When you have cross-core notifications, right? When the device interrupts, a process waiting for the device may become ready. And on the multi-core system, the process that becomes ready may belong to the affinity set of another core. Right? So you need to do this cross-core and cross-affinity set communication. But the multi-core hardware offers a way for one core to inform the other core that the process becomes ready. So you need to use these communication mechanisms. Pin interrupts. Right? So multi-core system allow OS to pin a specific service to a specific core. Right? You can see that okay, I have a daemon or service that I only allow it to run on core 1 or core 0. Right? And the device interrupts, only that specific core receive that interrupt. Other complications, right? Power conservation in multi-core OS, right? Because most processing is I/O bound, multi-core chips often has idle cores. That is so that I think that is one of the challenges that people have tried to address in early 2000s to I think probably past 2 decades. So since the 1990s or 2000s, CPUs become very, very fast. And because of this multi-core design, CPU becomes extremely fast, and I/O becomes a bottleneck. Okay, and a lot of the system design were driven by this imbalance. Right? CPU is the computation is very, very fast, but I/O is a bottleneck. And many of the system design is driven by this imbalance. Let me think whether there's a good example. Spark. Have people heard about Spark distributed system? So there is the system behind the Databricks. Have people heard about Databricks, the company? I think one of the biggest machine learning system company at this point, right? Although it's not IPO, but one of the biggest one. So Spark is a distributed system when it was originally designed that its core contribution is to keep all the data in memory. Keep all the data. Before Spark, there was a Google file system or Hadoop file system. And Hadoop computing framework. Those computing framework, they keep their data on disk, and only when it's needed, when the computation is really performing, they will load this data from disk to memory and do the computation. That is I/O. That is I/O. So Spark, its core contribution is to make sure that it maintains all the data in memory through its innovation. There's a new data abstraction that it designed, but that innovation ensures that it can keep all the data in memory and make sure that they are consistent across the entire distributed system. Okay, so that is a whole contribution, the core contribution of Spark, so that you're avoiding the I/O essentially. Right? You're keeping the data in memory, and the distributed computation framework can directly use these data in memory. Okay. All right. So it's I think if people are interested, the trend is becoming more. I think not it's becoming more interesting. So it used to be that network is slow. Right? So in the early days, 1990s or the 2000s, the network was slow, and people like to put data on their local disk in each machine. Right, so the first, you prefer to put your data in this tier, right? CPU cache, that's the fastest, and then memory, right? And then your local disk, and then over the network to some remote server. That was the old type, because network is very slow. But nowadays it's switched. Network is actually faster very often than disk access, right? Especially with RDMA, this kind of remote direct memory access, this kind of network protocol and hardware devices invented. Network actually becomes faster than disk access very, very often. And the recent trend, I think in the past 5 years, many of the system innovation, or if you look into the top conference publications, and this is the hot trend in the previous about 5 years. Right? How do you now that network is faster than disk? Right? How do you utilize this feature, right? To put your data? You prefer to put your data in the remote machine than putting the data on your local disk. Right? So this also changes the system design, and yeah, so that's another example. Okay. So the system design changes with the hardware ability. So that's if people are interested in system research, that's the two power that drives the system research and new software system design. One is the hardware is changing. The other is the upper level application is changing. Right? So when we just mentioned that because of the hardware changes, you can see new software system software research. And the other example is that because nowadays the machine learning workload is taking over, and people are designing new systems to support machine learning. Okay, and this is another trend. Machine learning workloads have very different characteristics compared to traditional workloads human generates, and this is a very different type of workload and requires a completely new design of operating systems, database systems, and distributed systems. People are redesigning the entire software stack to support machine learning workload. Okay, yeah. So these are the two trends, right? Hardware, application workload, and hardware. These are the two trends that drives system design. Yeah. So in my group, we are building new software systems for machine learning. If you're interested, send me your CV and transcript, and we can discuss what could be interesting research topics. All right. All right. So power consumption. Sorry. Back to this multiple OS. Right. On a multiple chip, having many cores running the no process idle is wasting power and reduces battery life. A solution is arrange a way for the OS to power down cores when they are not needed. Okay, but there are complications, right? Powering up a core takes extra energy. So if you always turn off and power up a core very frequently, it could be more expensive than if you keep the core idle. Okay, so sometimes it may be better to leave the core running idle for a short time and cycle through, then repeatedly power it down and powering it up. Okay, yeah, choosing the policy to do this power down and power up is not easy. Right, so there are many factors that complicate multi-core OS design, and a multi-core OS requires locking to synchronize among cores, and to avoid invalidating cache values, a multi-core scheduler must avoid moving process from one core to the other, and to optimize I/O processing and avoid all the cores receiving each heartbeat. They need to pin device to one of the cores and energy consumption, right? Yeah. So multi-core is, I think as I mentioned before, right? So this is just a brief introduction to multi-core, right? And the multi-core OS and distributed system, these topics are extremely complicated, right? So if you're interested, you can learn about multi-core or take my course next semester. I think we do allow undergraduate students to take that distributed system course, although it's for graduate students. But if you have taken OS, you satisfy the prerequisites, you can take 505. Okay. All right. That is multi-core OS. I think the last piece of OS that we haven't talked about is user interface. Right? So we talked about how to build the internal mechanisms, the functionalities, right? Scheduling and memory management and file system and device drivers, but we did not talk about the user interface, right? So we build an OS that does not have, that user cannot use, right? So that's what we have at this point. User interface is typically not usually not taught in very detail, but the reason is that usually when we teach user interface, we teach command line user interface. Right? So CLI, and CLI is a command line user interface. It's essentially a big infinite loop that provides a list of tools that you can use. And this list of tools that you use is programs that calls the OS functionalities, system calls. So that's a high level idea of a command line user interface. So it has a big loop, and this big loop is waiting for users' input. And when you type commands as user input, this big loop will interpret your command. And in Linux, right, if you type in ls, it was interpreted as you want to call this ls, this tool. And this tool is essentially a program that developer has written, and internally it calls the OS functionalities, file system, right? Because it's ls lists the current files in your current folder. It essentially will call the file system functionalities to give you the result. What is the files that exist in the current directory? Okay, that is a high-level idea of CLI, very straightforward. And but we'll look at how it's implemented. Graphical user interface is much more difficult, and we don't cover it typically in OS because it could be a different course by itself. Right? So usually you probably also need to learn computer graphics course so that you can better understand how graphical user interface is designed. Okay. Right. So two operating system interfaces. The operating system provides two ways to access services. One is an interface for the applications, right? The API, application program interface, or essentially a set of system calls the programs can use to write programs. Developers could use to write programs. Okay, and another interface is a human interface. In human interface, you can have a command line interface, a CLI, or graphical user interface. Right? And in the early days, there was only command line interface, and graphical user interface became popular in, I think, together with Apple, right? Apple's MacBook. That was when graphical user interface become popular. Okay. Yeah. So characteristics of user interfaces. GUI allow user to launch applications. May include copy paste and drag and drop, right? So you can see what you get. Right? So command line interface makes the file system visible. You can see what is the current folder you are in, and parse textual commands, and arguments passed to commands can allow the user to specify arbitrary level of detail. Okay. Yeah, so a command line interpreter. Software accepts commands entered by user and perform the specified action. So we mentioned, right? It's essentially a big loop. In every loop iteration, it takes the commands the user entered and interprets this command, and to find the correct program that is installed in the computer to execute your command. Okay. So two implementations of interrupter may have been used in early systems. Some small embedded system is the command interrupter is integrated into the OS, right? And Unix and Multics and later system, the command interpreter consists of an application that is separate from the OS. Okay. Advantage of a command line interpreter built into the OS. It understands common syntax and semantics. It can offer command complication capability, prompt for required arguments, check arguments for correctness, warn users for meaningless dangerous requests. But I don't think this is a unique advantage of command interpreter built into the OS. Right? So many application command line interpreters also have this ability. Okay. So this advantage, user is limited to exact commands for the OS provides, and the user cannot select a non-standard command interpreter. Adding new commands is difficult and require recompiling to OS. Right? This difficulty is real. So any new command is difficult, requires recompiling the entire operating system. So that's why the shells, like the Bash and Zish and Sish, I think these shells that you guys are using, they're not compiled into the OS. And otherwise, every time you update it, you need to compile the entire OS. Okay. Yeah. So command line interpreter implemented by application. Right, so after Unix, you have this command line interpreter that is implemented as an application. Right, so it only handles basic command syntax. Individual programs must check and interpret the arguments. The advantage is the user can choose their own interpreter. Right? That's why you have a variety of command line interpreters in Linux. Okay. And new commands can be added at any time. Right? You can even modify the program and add your own commands. Okay. Disadvantage, right? Non-uniformity among commands, arguments, no built-in semantic checks. Okay. But these are not the biggest blockers. Right? So nowadays, most of the CLIs are application level. Okay. I think next lecture, we will cover Unix shell and how a shell is designed in more detail. That's it for today. If you have answer questions, come on back and write your name. And thank you.